Dear friend, I am here with you to discuss a very good example for the calculation of deflection at tip of a cantilever beam by moment area method. This is my lecture 6 for module 2. In my lecture 5, you can see same example was discussed for calculation of deflection at point B through unit load method. I want to show its preview. We have followed this expression to calculate deflection delta B, which is a general expression for calculation of deflection at any point through unit load method. We need to find M1 and M2. Then there are two procedures we have gone through this one. We have just calculated M1, and here this was again the procedure continued for M1. Calculated M1 value was this one. Then we came up to calculate M2 value, and M1 M2 this was the M2 value calculated here. You can see M1 value was 1, M2 value is this. In integrating M1 M2 dx divided by EI integral 0 to L, we found deflection delta B WL to the 4 divided by 30 EI. This was the calculated value of deflection at point B. Now I'm going to find same calculation for deflection at point B, but right now we will use a method, moment area method, for the same example. I am using more than one method to for a same problem to make you aware, to make your concept more clear regarding the various methods, so that whatever method is convenient to you, if you forget any one of method during your examinations or doing analysis or designing any beam, you can follow any one of these. All these methods are very popular methods. Now we should proceed for calculation for deflection delta B through moment area method. Now what we do for moment area method, we follow two part for the calculation of delta B. First we find out M over EI diagram for this triangular loading, and in second part we find centroid of this triangular loading, and multiplying M over EI area of M over EI diagram with its centroid will give deflection delta B at tip of this cantilever beam. Now let's go with this principle to calculate M over EI diagram, then its centroid. Problem statement is here. This is beam subjected with triangular loading. Length of this beam is L. This point is A at fixed support, and free end is with B. Now delta B will be equal to area of M over EI diagram for this loading diagram, M over EI diagram multiplying with centroid will give deflection delta B at point B. Now we need to first find out M over EI diagram. I mean bending moment diagram will be divided with a constant value of EI, so that we will find a M over EI diagram. Now we will do first part. This is the second part. Now calculation for M over EI diagram. calculation for M over EI diagram. Loading diagram is here. It's a triangular loading. This point is A, this point is B, this support is fixed support, and the value, maximum value is W ranging from 0 to W. This is a triangular loading ranging from 0 to W. Here the loading is 0 and maximum value is at support. So this value is W. To develop M over EI diagram, we need to calculate bending moment profile. For that, we need to find first the general expression for bending moment. Let's say in a section XX, at a distance of x from point B, so that we will find moment mxxx, or you can say bending moment. Thereafter, after dividing m divided by EI, we will find the M over EI diagram. Now what will be the M over the bending moment? You can see, let's do it in the in separate part. Take this beam. One part of this beam is here, length is 0 to L, its value is W, and second part of this beam is up to section XX. Here there is a section XX, the distance is X. Now we need to find this value. Suppose this point is Y. Here we need to find this value Y. Now from similar triangle you can find this value, because this part is the same part. For this triangle we have separate out two triangles. You can also designate this triangle as triangle ABC, and this triangle is ABC, D and E. You can say this B, this is D, and this is E. Two triangle here, and this is A, B and C. Two triangle we have, and from similar triangle method, this is the triangle 1, this is triangle 2. Now from similar triangle W divided by L, W divided by L will be equal to Y divided by X, Y divided by X. Therefore Y will be W divided by L into X. This is the value, because in triangular loading it's a uniformly varying load. This is the uniformly varying load, or triangular loading is uniformly varying load. So every section from the point B will have a different value of load. So at a section XX, from a distance X from point B, will have a loading value Y. So loading value Y will be this one, W divided by L into X. So at a distance X equal to L, value of Y will be W divided by L into L. LL will be cancelled, so loading will be W. As per the expressions for the W, which we have shown through triangular loading having maximum value at support. Now we found out value of load at a section XX from point B. From point B, we have found out the value of load at edge Y. So bending moment at section XX will we have shown with mxx equal to m. So mxx will be what you can see here. This is a loading diagram. Section is XX. Section is XX. This point is D, this point is B, this point is E. Now we can show with a dotted line for the left part of this triangular loading. So for our proper understanding, this point is A and this point is C. Now this is the value of load at this is Y, and the section XX is at a distance of X from point B. So area of this loading will be what? Area of loading diagram EDB will be half into X into Y. Value of Y is W divided by L into X. So it will be half into X into W divided by L into X. So loading will be W X square divided by twice L. This is the total load. Area of loading diagram will give a total load in this triangular loading. If we take this, the area of this shaded part will give total loading, which will be acting somewhere at the centroid of this triangle. That will be as a point load, which value will be Wx square by twice L. Wx square by twice L. And this is nothing but the total load. Which will be acting at a distance of, you can say, this load will be acting at a distance of, since it's a triangular loading, its shape is triangular, so its centroid will be x by 3 from this section XX. It will be x by 3. So bending moment will be total loading multiplying with this centroidal distance will give bending moment at section XX. So now bending moment at XX will be bending moment mxx or m at section XX at a distance of x from point B will be mxx equal to total load multiplying with the centroid of triangular loading. Triangular loading up to section X to section XX from point B. We've calculated total load as wx square by 2. Total load is wx square by twice L, wx square by its centroid is x divided by 3. So bending moment will be wx cube divided by 6L. This is the mxx, or you can say m. At a distance of x from point B, we'll have a general expression for bending moment, which is a function of x cube. So bending moment diagram will have a cubical curve. It will be something like this. This point is A, this point is B, and this point is, and this value will be what we can find out from this. At x equal to 0, m will be 0. Putting x equal to 0, this value will be 0. At x equal to L, m will be w divided by 6L multiplying by L cube. L cube divided by L will have WL square by 6. This value will be WL square by 6. And this will be a cubical curve. You can say function of this curve will be x cube. So bending moment profile will have a curve which is a function of x cube. So we have calculated bending moment for this triangular loading. First we have developed a general expression for bending moment. Then after we have found out bending moment at support. This A is nothing at support of this beam, and B is the tip of this beam. So expression for general expression is a function of x cube. So it will be a cubical curve, and maximum value will be WL square divided by 6. Now we are going to develop a bending moment diagram dividing with EI, so that we will develop a M over EI diagram. Now M diagram is, bending moment diagram is this one, as we have calculated here. This is the M diagram. Maximum value is this one, W L square divided by 6, and length is L. This point is A, support point, and this point is B. This is the free end. Now M over diagram of this one will be, this is the M diagram. Now for developing M over EI diagram, M over EI diagram is nothing but dividing every coordinate y coordinate of this curve with the constant value of EI. M dividing by constant value of EI. This is nothing but a flexural. This is EI constant, is flexural rigidity of any structural beam, which is always constant. So M over EI diagram will be the, as we are going to divide every coordinate y coordinate by a constant value EI, the curve will have a same profile. This will be something like this, but its value will be, developing M over EI diagram, its value will be somehow less than this curve, because we are going to divide with a constant value of EI. This is the M over EI diagram. M over EI diagram. Because every coordinate is divided by constant value, so it will be transferred here, it will be transferred here, and so on and so forth. It will be transferred here. We will find the same curve. This is the curve. This curve will also be a cubical curve. cubical curve, or you can say this is a function of x cube. And m over I diagram, because the maximum value will be also divided by ei, so its value will be wl square divided by 6ei, and its distance is l. Now we have done with the m over ei diagram, so now I am going to find out the area of this m over ei diagram, and after that we will find centroid of this m over ei diagram, and multiplying area of this m over ei diagram with its centroid will give deflection at point B. This point A, this point at B. Now just come with the calculation for area of this m over ei diagram. Now we have developed m over ei diagram as this is the m over ei diagram. Maximum value is w L square divided by 6ei. This is the maximum value calculated here, m over wl square divided by 6ei, and length of this beam is L, and general expression for this curve is, you can see here, general expression function will be wx cube divided by 6eil, because every coordinate has been divided by with a constant value of ei. So we can say also function is a function of x cube. So as in my previous lecture I have given you a general formula for finding area of any curve, which is a function of any power from 1 to power n. Maybe a function x will be power of n. Then area for this curve will be this curve, which is a function of power n, 1 divided by n plus 1 base, multiplying base with height. For example, if we have a curve something like this, this is height h, this is, suppose this base is b, and this curve is a function of fx x to the power n. So area of this curve will be, this area of this other parts will be a equal to 1 divided by n plus 1 multiplying with b multiplying with height h. B is the base and h is the height, and 1 divided by n plus 1. As in this expression for m over ei diagram, this is the m over ei diagram. This is a function of x to the power 3, or you can say it's a cubical curve. So n will be equal to 3 as per the general expression of this one. So area will be 1 divided by n plus 1 base into height. This is the general expression for area from this, as I have explained here. Putting n equal to 3, we will find 3 plus 1 multiplying base will be L, and height will be wl square by 6ei, wl square divided by 6ei. So 1 by 4 multiplying wl cube, L multiplying with L square will be L cube divided by 6ei. So we can say wl cube divided by 24 ei. This is the area of this. This is the area of this m over ei diagram. This area that I am shading here, this is the area of this m over ei diagram. Now centroid of this m over ei diagram will be, it will be, this is the point B, this point is B, this point is A. Centroid of this M over E diagram will be acting somewhere at a distance of x bar. It will be designated x bar. Now we need to calculate value of x bar, so that we will multiply area with x bar to find the deflection at point B, which will be delta B. Now this is the M over E diagram. Maximum value is WL square divided by 6 EI. Length of this beam is L, and area calculated here is A equal to WL cube divided by 24 EI. This is the area. Now we are going to find centroid. This point is A, this point is B. Now centroid will be of this triangle. This curve will have this centroid. From the general expression, this curve has a function of x to the power cube, x to the power 3. Function is x to the power 3. So from the general expression of fx x to the power n, we have a general function fx which is a power of x to the power n, and this curve is this is h, this is b, and this function is fx x to the power n. So centroid from this point B, suppose this point is A, this point is B, centroid x bar will be what? X bar will be n plus 1 divided by n plus 2 multiplying with base length B. This is the general expression for any function which is the power of n. So from as this curve is a cubical curve, so here n will be equal to 3. So centroid x bar will be n plus 1 divided by n plus 2 multiplying with this b. Here b is nothing but b equal to L, n equal to 1, n equal to 3. So 3 plus 1 divided by 3 plus 2 multiplying with this base length L, b equal to L. It will be 4 divided by 5 into L. Here we have done with the calculation of x bar. Here we have found out area of this M over E diagram. So delta will be A multiplying with x bar. Area calculated is WL to the power 3 divided by 24 EI, and x bar is 4 divided by 5 into L. So delta will be, in place of A we will put W L cube divided by 24 EI, and in place of x bar we will put this value 4 divided by 5 into L. 4 divided by 24 will be 6. So it will be WL to the power 4 divided by 30 EI. This is delta B. This is the calculated value for delta B at point B for a cantilever beam which is subjected with triangular loading. So we can say delta B is WL to the power 4 30 EI. Same we have calculated deflection delta B at tip of this beam, tip of a beam which is subjected with linearly varying load, or you can say triangular loading using unit load method, and value calculator was same as WL to the 430 EI. That same example was solved with unit load method, and value calculator was here WL to the 430 EI. This is the value for deflection. You can see lecture 5 of module 2 to go through with the same example with unit load method. I hope the concept regarding moment area method might have cleared, and we will solve the same example through conjugate beam method. Keep watching and keep sharing to your friends and colleagues, and please subscribe my channel MSA Structural Engineers. Thank you so much.